All right, welcome back, everybody. Today's part of the book is really short, so we're going to switch over to a website that I like about halfway through to get some practice with these. So we're going to be focusing on spherical coordinates, and thankfully this is the last chapter, or the last section in chapter 13. And we're going to move over to PDEs pretty soon. But we want to talk about spherical coordinates because this is just like cylindrical coordinates, except for sphere instead. And I just want to describe why maybe we should care about each of the coordinate systems, so I'll just mention that again. And I know I kind of covered this already, but let's just jump back. So, why are these coordinate systems important? Let's just look at Cartesian. For example, look at the room you're in. It's approximately a cube. In some sense, Cartesian coordinates are basically saying it's the cubic coordinate system. We're trying to consider cubes here. In a cylindrical coordinate system, think about pipes, your sewage pipes, your water pipes. You're thinking about electricity through a wire, especially like the magnetic field, which would result from the wire. As electricity travels in one direction through the wire, we get kind of a rotational magnetic field around the wire, and that's going to be easily representable in cylindrical coordinates. And then jumping to spherical coordinates, well, if we jump out far enough, where do we live? We live on an Earth, and that is a sphere. So, we live on a sphere, and then also if we look at atoms, or even electrons, individual particles. Any individual particle with a charge is going to have some sort of spherical symmetry to it, and so depending on whether we're not talking about electricity through a wire, or maybe just a single electron with a charge, we're going to want to use a different coordinate system. And Cartesian, being the one that we kind of grew up with and that we're very used to, turns out not to be terribly useful in a lot of physical applications, because if we're dealing with anything gravitational, even the forces in general, anytime we have a force that's produced, it's almost always produced spherically. And so the spherical coordinates are very important for that. Cylindrical coordinates are incredibly important anytime we're dealing with electricity through a wire, or even any other sort of kind of restricted flow system, right? That's what we want to think with cylindricals. If we're restricting the flow of an object in a single direction, then often it's basically favoring the one direction it's moving in, and then it has some sort of symmetric property in the perpendicular plane to the direction it's moving in. And so that's why cylindrical are very important. So this is just kind of jumping back, saying, yeah, these are all going to be important. Definitely spherical. Once you get into physical chemistry, you start to talk about electron orbitals, of course. And I know in general chemistry, you also consider orbitals, but in physical chemistry, you can actually start to calculate the shapes of those orbitals. And you're going to calculate them in spherical coordinates. There's not really another way to do it. So that's why these are very important. So let's just look at how maybe we define spherical coordinates. And what we're going to do is unfortunately, I'll jump back up to those definitions earlier, but let's look at the nice sphere here. So unfortunately, there's now two angles that we have to keep track of, right? In cylindrical coordinates, there's really only one angular direction we can rotate in, but in spherical coordinates, there are two angles we can rotate in. Think about these angles like, latitude and longitude. Angles, have you ever wondered why they say, 30 degrees north, 60 degrees east, or something like that for your latitude and longitude, that they are, in fact, angles, right? Both of them are angles. And then we talk about the radius. So this should actually be an R here, as well as radius. So we have two angles, which correspond to latitude and longitude, and one radius, which corresponds to how far out or in am I. If I wanted to uniquely specify a point on the surface of the Earth, I only need the two angles. That's why I need latitude and longitude. But suppose I were either flying in an airplane, or in a submarine, or perhaps even digging down towards the surface of the Earth, then all of a sudden I need a third coordinate which describes how high I am from the surface, or even in fact how far I am away from the center of the Earth. So that's where our three coordinates are going to come from in spherical coordinates. And if we jump back up here, we notice that theta, so we're keeping theta. Theta is kept from cylindrical. This is the same theta as cylindrical, but now we're adding on phi. Okay, so phi describes, if theta was telling me my angle through the xy plane, phi is now describing my angle away from the z-axis. So basically I'm asking myself, I'm going to start at the North Pole. How far is my angle away from the North Pole? That's another way of thinking about it. Start at North Pole, right near Santa. How far an angle have I moved down south? So if I start at the North Pole, how far of an angle have I moved south? That's what phi is going to describe here. So theta is still describing me away from the x-axis. If we jump back to cylindrical, that was away from the x-axis. And now phi is going to describe how far away from the North Pole I am. And then r is no surprise. R is the total radius. We'll say sphere radius. Or in other words, how far in magnitude from the origin am I, right? I can either be really close to the origin, r is going to be small. I can be far from the origin, and r will be large. But we use these definitions to describe those, and so it's just good to memorize all of these definitions. Let's check something really quick. So we would want something like r squared to be x squared plus y squared plus z squared. And let's just verify that that's true. So x squared would be r squared cosine squared theta sine squared phi. Y squared would be r squared sine squared theta sine squared phi. And finally z squared is r squared cosine squared phi. If I add each of these together, each one has an r squared, so I'm going to factor that out. And then I'm left with cosine squared theta plus sine squared theta. Hi, kitty cat. That's my kitty cat. Times sine squared phi. And then I'm going to add cosine squared phi. And if I work in steps, I can use the Pythagorean identity on cos squared plus sine squared there and receive 1. But all of a sudden that means I have a 1 in front of sine squared plus cosine squared, and I use the Pythagorean identity again, and I recover r squared. So this does work if I add x squared, y squared, and z squared together. Okay, so these are the definitions. Basically, we kind of have to memorize them. I mean, they make intuitive sense, because if we get rid of this whole sine phi, cosine phi business, then we kind of recover our cylindrical coordinates, at least in the xy plane. But then we modify with the sine and cosine phi. So I'm going to scroll down, and maybe I'll talk about this really quick. So if we want to jump back, how do we find phi from x, y, and z? Finding r theta phi from x, y, z, that hasn't been described here yet. R is, we just noticed, x squared plus y squared plus z squared, and we take the root. Theta hasn't changed from before. It's the arctangent of y over x, possibly plus pi, depending on how your calculator interprets arctangent. And finally, phi is a little bit trickier, right? But if we look at root x squared plus y squared over z, we'll end up with an r sine phi in the numerator and r cosine phi in the denominator, and so we'll recover tangent of phi. And so actually we can find phi with an arctangent as well. Arctangent, a little bit tricky, root x squared plus y squared over z. And then this, similarly with your calculator, may need to be added with pi. So that's how we would reverse the three of them. Let's scroll down to integration with spherical coordinates. So we can do the same procedure we did before with cylindrical coordinates, where we understand their definitions, and we compute the differential of the transformation, which takes us from an xyz coordinate system to an r, phi, and theta coordinate system. And we recover the Jacobian of that, and we take the determinant of the Jacobian to recover r squared sine phi. Okay, so that means if we are writing in one sense dx, dy, dz as the volume form in Cartesian, we're actually going to pick up an entire r squared sine phi in spherical coordinates. So that's just something to keep in mind. Don't forget this when integrating. So if we construct an integral in spherical coordinates, we have to remember to add an r squared sine phi into our integral. Okay, so I'm going to jump over now to that website because the book ends the chapter here without any examples, and I'd like to go through at least one integral example in spherical coordinates. Okay, so here we are on the website. It's called Paul's Online Notes. You can definitely come here periodically. I like these notes for calculus help. And so here we see kind of the spherical coordinate system that I just covered. According to our book, you can see they're using a variant on phi. That's also phi. So there's two versions of the Greek phi, but they're the same ones here. And then they're using rho instead of r in this case. And that's not a huge deal. Obviously, r and rho are the same, plus or minus a Greek versus Roman alphabet. Okay, so if we jump down to this first example, I'm looking at example 1 here. It says evaluate the triple integral of 16z dv. That's going to be like our d omega, where e is the upper half of the sphere, x squared plus y squared plus z squared is 1. So I want to sketch out, let's integrate. This is going to be the upper half of the sphere. It's the upper half of the sphere, so this is like x squared plus y squared plus z squared is greater than or equal to 1. And then in particular, the upper half would be that z is also greater than or equal to 1. And then here we have 16z d omega. Now I need to convert this into spherical coordinates. So this first part, greater than or equal to 1, is really useful for me. I can think about that in spherical coordinates as saying that my radius is going between 0 and 1. And I can think about the upper half, z greater than or equal to 1. Okay, so z greater than or equal to 1 corresponds to phi, which is, recall, phi is the angle between, or I guess angle from z axis, and I would do a quarter rotation. So hence, for the upper half, right, the upper half sphere, a quarter rotation is pi over 2. So phi is going to be going from 0, pi over 2, and theta, which corresponds to my rotation in the xy plane, will be going from 0 to 2 pi, because I have a full rotation in the xy plane. So that's where I can find my bounds. And so if I rewrite my integral in terms of, let's say, phi, theta, r, the order doesn't really matter. Phi, theta, and r, I know phi goes from 0 to 2 pi, or sorry, pi over 2, theta goes from 0 to 2 pi, and r goes from 0 to 1. And then I can't forget r squared sine phi. And then I have my 16z over here, but recall z is r cosine phi. So really what this turns into, if I simplify a little bit, I have my triple integral. I'm not going to rewrite the bounds, but I have 16 r cubed cosine phi sine phi d phi d theta dr. So this is the integral I'm then going to compute. I'm not going to go through this by hand because we have Wolfram at our disposal. In particular, it's this cosine sine term. It's not that hard to do. You would use a u substitution on cosine sine term. You would choose that sine is u and cosine phi is du, and then you would use u substitution. You recover sine squared. But we can talk more about that in class. But anyway, this is how we would set up the integral, and then we would compute just in terms. So I wanted to make sure that we didn't forget this r squared sine phi, and then we also have a little bit of practice talking about these bounds. Okay, so I'm just going to click on show solution really quick, and they're going to find the same bounds that we had. So the bounds for rho are 0 to 1, the bounds for theta are 0 to 2 pi, and the bounds for phi are 0 to pi over 2. So we've got the same bounds there. If you go through the integration, you would get 4 pi. We're going to move on to the next example because I like giving you all enough examples here. It says evaluate the triple integral zx dv, where now e is inside the sphere of radius 4 and the cone that makes an angle pi over 3 with the negative z axis. And then x is negative. So this, we need to get a little bit more complicated when we draw it out. let's draw in 3 dimensions. I'm going to construct my sphere of radius 4. Let's see how good I am at drawing spheres. My sphere of radius 4. I'm going to draw something like that. That looks pretty good. So there's my sphere of radius 4. I then have to consider this angle of pi over 3 with the negative z-axis. So there's my negative z-axis points downwards. Pi over 3 is something like that from the negative z-axis, right? So I'm going to call that distance pi over 3. And then x is negative. So x is negative corresponds to the left-hand side here. So I'm going to chop myself off. I have my little cone there, and I chop off at the x-axis. And so I'm basically considering the bottom left cone here, just like that. Cone with a rounded top, I suppose, so like a weird half ice cream cone shape on the bottom of the sphere, and I have to think about how that corresponds to my bounds in spherical coordinates. So let's see. What are my minimum and maximum values for my radius? Well, my radius still goes from 0 to 1. That's easy enough. The bounds on theta are a little bit tricky, right? So if I have the negative x-axis and theta starts, let's just draw the xy plane. This is the x, let's say xy plane, and theta starts here and starts wrapping around. Then the negative x-axis is this area, right? So this would be theta from pi over 2 to 3 pi over 2. And finally in phi, if I want to construct bounds in phi, this helps me out a little bit. The angle of pi over 3 with the negative z-axis. If I start phi all the way up here, that's phi equals 0, but I don't want to consider the top part. I'm starting right there, and I'm finishing it off to the negative z-axis, which is when phi is pi. That goes from pi minus pi over 3, also known as 2 pi over 3, up to pi. And so those are my 3 sets of bounds. And these problems are a little tricky, right? Because the bounds are always what makes our life hard. Those are my 3 sets of bounds. Let's set up the triple integral then. Triple integral r squared sine phi d, let's say dr, d phi d theta. I don't really care about the order. Dr, r goes from 0 to 1. D phi, phi goes from 2 pi over 3 to pi. And finally theta goes from pi over 2, that's a pi over 2 up to 3 pi over 2. And then what goes inside my integral is right here, zx. And if I recall the definition of z, it's rho cosine phi, and x is rho sine phi cosine theta. I'm going to recover, I guess, r squared sine theta cos phi sine phi. That's going to be my x and z. And once I set that up, then I can compute the integral. So these problems are tricky in how we actually set them up. They're not really tricky for other purposes. So let's see what the answer they get in that case is. My bad. So they'll notice this is my fault. The radius should definitely go up to 2. That's because we're the sphere of radius 2 over here. So that was my bad. You should definitely go up to 2, and then you can see phi is going between 2 pi over 3 and pi, and theta is pi over 2 to 3 pi over 2. And so if you go ahead and go through the work to compute that, you get 8 root 3 over 5. But once again, we have Wolfram at our disposal. All right, so that's all I have. I know these are a little tricky to set up because we have to start thinking more and more in 3 dimensions, but I think we'll get there. Thanks. Bye.